started in this lecture. So what is the bi-model? So as Stas mentioned, we want to deal with particles that have interaction. So we don't know how to write a partition function for a gas or material which has interaction in it. So the problem is that we cannot factorize our bi-party partition function, even if we will be able to calculate it. So we need to think of some kind of other method so that we can be able to factorize the partition function. And the bi thought of a model that helps us to do it. So basically, the model says that we can take some a gas or some lattice that have interactions between atoms. So you can think of a gas that have some lattice, that have interaction between atoms inside of it. Some kind of interaction, it doesn't matter. And then if we do some exchange of variables to the coordinates, then we can separate the interaction, and then we can write down the partition function and factorize it. Okay, so I hope that the idea is understood for everyone. If you have any questions, so please ask me. So to begin with, let's start with let's assume that we have atoms and each atom is vibrate near its equilibrium. So we will denote the xi coordinate as the displacement of the I atom from its equilibrium. Then we need to assume that we have some kind of potential which goes from one atom to the third end, okay? And now we want to expand the potential near the displacement, okay, near its equilibrium. So we are able to write it down as follows. I think there is a factor right here. That's you know, of the order of xi, xj, xk, and etc. It doesn't matter. We are just want the first contribution from the Taylor expansion. So we want only we are near equilibrium. So the first derivative is obviously 0. So after we got this, we can write the Hamiltonian. Okay. H, as you know, is the as you know, H is the plus V of X. So we can write it as sum of I, X dot I plus 1/2 and Aij. So this is the Hamiltonian. We can neglect the V0. It's just a constant. It doesn't matter. And Aij is just the coefficient of the derivative. So it's just okay. So Okay, next. So as you see, there is interaction, okay, between the atoms. So basically, we can always diagonalize this matrix, right? We can always write the matrix as S, D, S minus 1, where D is diagonalized matrix, okay? So we basically can write it and then plug it in here. I skip it, but it's written in the tutorial, so you can follow later. And I will just write down the final answer. So we can present a new coordinate, Q, which is X times S, okay? And then we can write H as V0 plus sum of I m over 2 qi squared dot plus dii qi squared. So if we define that dii is equal to m omega I squared, then we finished, right? Now we have a theory that describes just a summation over harmonic oscillators, right? And basically we finished now because now we are able to write the partition function, and we can factorize it. So we are done. So what we got here? Okay, what is the coordinate qi? Can someone tell me? From what Stas told you, maybe, or maybe you know from other courses.
The linear summation over all the states.
Okay, but what is its name? Yes. So basically, this is a quasi-particle, which we call phonon. Phonons are the vibrations of the interactions between the atoms, and each phonon has its own frequency. For each phonon, we can relate another omega. So, okay. So the meaning is that we want to write that the atoms are moving. Each omega is that all the atoms are moving with the same frequency. Okay, is it clear? Okay, so if there is no questions, I'm assuming that yes. So now we can also write the energy, because it is just energy of an harmonic oscillator. So E is equal to V0 plus H bar omega I. Okay, so this is the energy. And it's important for you to note that each I denotes excitation, right, from the ground state of this system. So we can have several phonons which are from the same kind, from the I kind, and for all of those there is the same omega I, the same frequency.
But isn't each I describe one phonon?
No, each I describes a frequency, but we can have several phonons that yes, they are the same kind, but okay. So now we don't have interaction, as we said, and we can finally we can write the partition function. Okay, so what is the partition function? By definition, it is just sum over ni from 0 to infinity, e to the minus beta of course that I just neglect it, okay, because it doesn't matter. Okay, so now it's just okay, so we know the solution for this.
This is the partition function for a single
Yes.
particle.
Yes. This is for single phonon. Yes. So now this is just equal to okay, and as you said, this is just the one partition function. So the total partition function is just, I really don't know how to write all those z's. So it is just z. This will be zi. Maybe I will write it as zi. Okay. So now we have the partition function, and we can try and we can start and calculate different quantities. So
But we still don't know the different omega i's, right?
no, we don't know them. We don't know them, and this is just the next step, because we need now to weigh them. As we studied last week, now we need to weight each omega i's and this contribution to the total system. So we will use the density of states, okay? But this is חזון למועד, שאומרים באנגלית. So now we basically, after we have the partition function, we have everything, we finished, you might say. So now let's calculate the free energy. So the free energy is just KB T ln Z. Okay, so we know this, we know that. So it is just equal to minus KBT ln so we can write it just as okay. Now, as you mentioned earlier, we need to weight all the omega i's. Okay, so we need to use the density of states that we studied, and it will be from integration. Okay, so this is it. Everything is fine? Okay. So this is the free energy. And now what is left for us to understand is what is the d of omega? What is the density of states? So
Why can we move from summation over 3n things to an integral?
why you can do this?
From there to there. Why can we do this? Because this is something badid.
Yeah,
this
discrete.
is continuous.
Yeah, this is discrete and this is continuous. But if I am assuming, for an instance, I can assume that each omega is very near to each other, and then I can take it into the continuous limit. I mean, in your first year, you studied that how you perform an integral. You have a Riemann summation, right? And then you said, oh, they are really tiny. The difference is really tiny, so I might take it just to the continuum limit, and this is just the same end waving that the physics like to do. Okay, so in the bimodel, we are assuming that the density of states, we have several assumptions. Density of state is linear. Which is the form of what? Density of states. And this is this is the density of states. Okay?
Okay, thank you.
Okay. So but we have the generation of level 3, right? Because we have in this lattice we have two longitudinal, two transversal directions and one longitudinal, right? You know what I mean? Yes.
Second.
We have the generation nivun of level of 3 because we have wave vectors that is longitudinal, okay, and two that are transverse on the plane, okay. So I think you calculated this. If I have time and you don't know how to get to this expression that I will write now, I am willing to derive it later. But the density of states is just going to be it's just going to be 3v omega 0 over 2 pi squared dx squared and 0. Okay, so we need to have a cutoff frequency. And why is that? Between two atoms, the two nearest atoms, they have wave vector, right? That is k equal to 2 pi lambda, right? But lambda it can be smaller than some typical value, right? Because the two atoms cannot get near closer than some distance. Okay, so we need to have a cutoff that above this frequency, because remember that the frequency and the wavelengths are opposite to each other. That above some frequency, we have density of states of 0. So this is why I wrote this, because of this cutoff frequency. And this is the frequencies that can have for the density of states below this frequency. Okay? So you might want to ask, but how do we get this frequency, which we call omega dBi? So we know that the degrees of freedom that we have, that if we will sum over from 0 to omega dBi, this maximum cutoff, and we will sum over the density of states, then we must get 3n, right? Because this is the number of degrees of freedom that we have in the system. So as it turns out, you can just write it in here and to plug it in. Omega dBi is equal to Vs is it okay for you, or you need me to write more explicitly the terms and develop them? It's fine? Okay. Any questions until now?
The WB or WG?
What, this? Oh, yeah. This is WD. Okay. This is also WD.
The expression for DW is given to us, right? We didn't.
The expression of DW?
Yeah.
No.
It's just given to us.
No. No.
So
We can derive it. I think that you derived it in the lecture, but if not, I can derive it again for you if you need after I finish the material. Can I erase this? I hope the answer is yes. Because I already erased. Okay, so let's do some example. A, find an expression for the energy of the lattice according to the values. Okay, so basically we know that what is the energy, how we find the energy, and as you know, I hope you know, is minus okay, so it basically needs to just calculate this, right, the dashed line. So now, this everything is continuous, and whatever you need to justify it, and then I will just write it like this. I can replace the derivative and the integral order, and I will remind you that this term, ln of z of omega is equal to e minus beta h bar I over 2 divided by 1 minus. Okay, so we need to take the derivative of this. I can do it, but you want me to do it, or it's okay if I will just write the answer?
If someone else did it,
Good. So this is just u and beta just 3 volume h bar divided by squared. Let's say I think there is a mistake here because this I think there is a mistake in the derivative, right? Because this must be omega over. מה זה?
זה לא צריך להיות לאן של...
This?
כן, כאילו כל זה...
Oh, right. This is LAN. Sorry. Okay, no. Let's say it's home. No, now it's now it's fine. Okay, let's just take the derivative. So this is a ln of e to the minus. This is just minus beta h bar omega I of 2 minus ln 1 minus. Right? And if we are taking the derivative, so this is just minus. Oh, but it's minus minus. Okay? It's minus the derivative, but minus all that. So it's minus h bar omega over 2 minus beta h bar omega e to the minus beta h bar omega I over 1 minus a. Right? And then we need to multiply this by yes, that's it. Okay. Because the DOS is omega squared. Okay. Did you all follow? Okay, so now this is omega divide. As now, as always, we don't know how to calculate this term explicitly. It's very hard. So we can do some. Basically, this is a final result. Okay, if you are asked in the exam to calculate U, So this is the final result, and it's fine. You can show it like this. We know how to calculate it only in some limits and under some assumptions. So let's mark this expression. Okay. Okay. So now we have this, and we are happy, and now we want to show that the limit that beta is much larger than 1, you can get Stefan Boltzmann. So it starts to talk about the Stefan Boltzmann law.
I think so.
Okay, so until we will speak about this and we'll explain it formally, then all you need to know is that u goes like t to the 4th power. That's it. Okay, so we take this integral, and then we will do exchange of variables. So we define this. So d of omega is dx beta h bar, and x ranges from 0, beta h bar, omega divide. And let's write this. Okay, let's write this. So now u is 3vh bar, 2 pi squared vs squared, 0 pi plus no. Well, plus okay. Now we have the assumption.
הוא צריך להיות h בר במכנה הראשון, בלי בריבוע h בר?
כן, יש פה. דבר ראשון במכנה.
אז ה-h בר בלי בריבוע.
למה?
יש, איפה ל-h בר?
תודה.
אבל זה היה אמור להיות אומגה בשלישי.
לא, זה אומגה בריבוע.
בסדר, עם היחידות.
אומגה בשלישית את אומרת?
אני חושבת. כשהם פוסלים לפי בית הזה, h בר אומגה והסקופ.
רגע. כן, זה h בר בשלישית. בגלל זה ואז גם זה בשלישית. אוקיי.
היית כבר בריבוע עכשיו.
נכון. תופסים אותי כל הזמן. טוב. אוקיי, so now I want to neglect this term. Okay? Because it will contribute less than this, and I want to get and I want to be able to solve the integral, and I want to take this because beta is greater than 1, so I have the assumption that beta h bar omega is also greater than 1, so this integral goes to infinity. And I won't be able to take it to infinity if this not goes to 0, because then it will diverge. So it is just okay. And this solution, this integral as a okay, this integral has a exact result. It's 5 to the 4th over 15. So the result is just some constant. I don't care. And this is exactly what we wanted. Okay, and now we want to calculate the heat capacity. Oops.
Why is the expression with the
What?
how do we get to beta to the 4th?
1 over beta is k Boltzmann T. Right?
No, I meant how we got to the 4th. But I understand. Okay.
Here, beta h bar to the 3rd, and from here, another one. And this one I took to 0. Okay, what is the heat capacity? So the heat capacity is the U to the T, and it's going like the temperature to the 3rd, and I think, and as you know, how did the Einstein model failed? Because experimentally they saw that the heat capacity goes like to T to the 3rd. But Einstein, if I remember correct, it went like T to the square T, right? Something like this. And at low temperature, yeah, it's low temperatures. So this is how the Bayes model matched the theory. Okay, so this is it. And now, in the time that we left, I want to speak about black body radiation. So a black body is an object that absorbs whatever it goes perfectly, and the emission depends only on the temperature. Okay, so of course thermal equilibrium and all these assumptions.
The temperature of the object is constant.
What?
The temperature of the object is
The temperature of the black body. Temperature of the. I think
It loses temperature via radiation.
I think that no, because it loses radiation to the environment. So it depends of if the black body is the bath or the system. If it's the bath, then I assume that not. But if it's the system, so it might be. But I think that we are in thermal equilibrium, so there is no meaning to temperature, right? Because constant time. Okay, so the dispersion relation is just CK. And this time we don't have, black body radiation is described, black body radiation described by 3 phonons. Okay, so because we are dealing with 3 phonons, there is no omega debye, there is no maximum cutoff. We can take each frequency we want. And there is only 2 polarization directions. Someone tell me why? There is just G is equal to 2, while in here G was equal to 3. What is the difference between the bimodal and black body radiation? We have the same dispersion relation, right? Linear. But this time we just have 2 generation, which is K transverse and K transverse. But we don't have longitudinal wave vector. What is the reason?
because it takes all the energy. And
No. I remind you that we
Gets
are dealing.
absorbed.
What?
There's what that goes out, and there's what that.
No, I will remind you that we are working. Black body radiation is electromagnetic, right? Waves. So there is no longitudinal waves in electromagnetism, right? Only transverse. So that's the reason. And the density of state is just V omega squared pi squared C squared, and F, I will write it here, is just F goes as KBTV over pi squared C third, 0 to infinity. The omega, and the U is just dot. And I will just write the final result. You can check later. And this is the Stefan-Boltzmann law, where you will see later that in astrophysics, and when you work with this quantity, then you call this sigma. That's it. Any questions? Okay, so we finished. If you want, I can show you how to derive the density of states.
no, I think I'll get it.
Sure?
אני רוצה לראות אותך.
You want to see? Okay. So I will do it. Okay, so basically we finished. Whoever wants to leave may leave. I will show you how to derive it. Okay, so as you know, omega, the density of states is just 1 over this 4 pi third r to the power of 3, and the radius is just the volume right? I am taking this. This is just n. You can think of it as the quantum number. Okay? Good. And now you want to take the derivative of this to get the density of states, right? Density of states, the derivative of this. So d of omega is just what? What is uniform? Nothing is the density of state. The number of states is just the volume of the sphere where we have all the states, right? So this is the volume, and this is what the radius is, because we recall that we are dealing with in the Debye model, so the atoms cannot escape the lattice. So K is just pi n over L, right? This is just what I written here. It's the same, okay? So now we need to take the derivative. So 2, right? So d omega is just pi over 6, 3 r squared, and dr d omega. Okay. Now now it is just d of omega is just pi over 2. R is this, and it is just the volume over pi squared, okay, because this is r squared, 3 to the 2/3, and pi. So pi squared, so you understand why I wrote 3 over pi squared, pi third? Yes, okay. And now there is the trick. So the trick is that K is equal to omega over C. But we have 3 directions. So we need to write it carefully, and we need to write it as follows. This is KL, so KL, the omega, plus 2KL, and squared, so KT, the omega. This is the expression, okay? The longitudinal directions, and this. So KT just this, and KL just omega CL. Fine? And now we just got that this is V over 2 pi squared, and KL is just omega omega to the power of 3 over CL3 plus 2 omega to 3 CT the third. And then we can just give some definition that 3 over C tilde is by definition 1 over CL3 plus 2 over CT third. And then we just get this density of state. Okay? It's the same. You see? And for the black body radiation, then we don't have this. And then when I wrote it, I don't know, I think I reversed it. But here. But for the this is if this is 0 because we don't have longitudinal waves, so we get this. But in the other case, it will be 3 over 2, I think. And so DO is equal to 3V omega squared, 2 pi squared. Okay? So, any questions? Okay, so have a nice week. Bye bye.
יש לי גם שאלה